We're going to be continuing our session. The next speaker is Dennis Hore. I hope
That's good. Perfect. It's perfect.
Okay. Yeah. Enhancing molecular structural information in nonlinear vibrational spectroscopy. Okay.
Great. Well, thank you very much. So I don't have any photos here to show, but I'm going to tell a story. And so I was a postdoc in Jerry's lab, and of all the things that were great about that experience, one of the things which I didn't take for granted on a daily basis was just the group, how great the group was and how tight-knit the group was, and just supporting each other, not just with discussions about the science, but help on the instrumentation. And it was just so fantastic. And I've always been very curious as to how could it have been so good. And people have these theories that like attracts like, and but I thought it was because of Jerry somehow, but I could never really figure out what she did to make the group so awesome. And once in a while when she'd be recruiting students, I'd really try to pay attention to see, but I couldn't figure anything out. Like nothing seemed out of the ordinary then as well. And it really puzzled me. So I have so my story is that when I joined the group was really big, and there weren't enough desks for everybody. So my desk was off to the side in a kind of overflow area where some of us were. And then after some time, one of the desks in the lab, in the main kind of hub of things, freed up when one of the students graduated. So I thought, oh, perfect, maybe I can move there. So I came to Jerry's office and I said, hey, Jerry, can I take this, this desk that's freed up in this office? And she said to me, Dennis, it's possible that you can take that one, but I'll really have to think about it, because I really think about where people sit for the kind of dynamics. And as soon as I heard that, I thought, whoa, like this algorithm is definitely way above anything I'm able to understand. So Sharon had a slide of some of the things she learned from Jerry. So this is one of the things I admired but never did learn from Jerry. But we all appreciated it because it was a great experience, even if it was for very complicated reasons we won't understand. So I'm going to tell you a little bit about some of the research areas in my group in Victoria. So there's kind of three themes of things we're working on right now. The first is we're interested in characterizing some materials which have applications for electro-optics, various regions. And Bruce, I was laughing because you were going to make fun of me that I've got wavelength and microns labeled here in the infrared, but there you go. And another area of interest is looking at chiral thin films, or materials which are organized like cholesteric liquid crystals, which are really good discriminators of left and right circularly polarized light. And the third, which is probably the largest area, is looking at solid-liquid interfaces. So various types of spectroscopy, mainly linear spectroscopy in all these fields. But we're also using vibrational SFG to look at solid-liquid interfaces. So I thought this would be fitting for me to talk about today, because it's because of Jerry that I inherited my interest and love of vibrational SFG. Actually, when I left her group, a parting gift, I got this I Heart SFG t-shirt. And I was going to wear it today, but I've realized that people think it's very strange. And I used to just wear it not knowing what's going on. And then I'd be in the grocery store, and the cashier would be asking me about what I Heart SFG is. And I think the problem is my explanation would be like 20 minutes long, and the person after me would want to buy their groceries. So I didn't wear it today. But so I'd like to talk about some of our work in the SFG area. So one of the reasons why the solid-liquid interface is so complex and really eludes structural characterization so well is because there are a lot of different interactions that go on here. So we know that in the solution phase, there's interactions between the molecule and the solvent, and the solvation of those molecules is really responsible for the shape of those molecules, in the case of complex molecules like proteins for their secondary and tertiary structure. But once you have adsorption on a surface, you have more interactions that come into play. So for example, you have specific interactions between the molecule and the surface, which can change its orientation and also its conformation on adsorption. But you also have the interfacial solvent environment, which provides that kind of which provides the local neighborhood for molecules. So basically, there's a lot of different types of interactions, and characterizing the structure of the solid-liquid interface really involves looking at all three of these aspects. I'm going to talk about a couple of them today. I'm not going to talk about the water. So Jerry's provided an introduction to the techniques. I'm not going to talk about the nuts and bolts of SFG. So it's basically like the more familiar electronic second harmonic generation, but the non-degenerate form of this spectroscopy. And so we're doing this with a 532 nanometer fixed visible, and all the materials I'm going to talk about are very transparent in this area, so we don't get any electronic resonance at all. And in the experiment, what happens is we basically tune the energy of the IR beam. And as the IR beam energy gets close to and matches some of the vibrational resonances, then we have a resonance enhancement in the signal. So this is basically the nature of the spectroscopy. And as a result of this, you can get spectra which are very sensitive fingerprints for what happens at the interface. But one of the questions that we're interested in is how can we take these fingerprints and turn them into a structural picture of what's happening. So I'm not going to talk about the details of how we go about this, but I want to just give you a one-slide overview. So all of the techniques I'm going to talk about have basically 3 steps in common. And the one step is that you measure the spectra, the vibrational SFG spectra with different beam polarizations. And this gives you information about how the molecular orientation is projected into the lab frame. And the second step is you need to know something about the vibrational modes themselves. So you need to have some idea of what the hyperpolarizability is, either from a depolarization ratio in the Raman to help you out or some calculations. And then once you know these 2 things, the name of the game is to put these 2 things together in the context of what is the distribution of modes at the surface, which has resulted in this average that you see in the experiment. And that's where the structural information comes in. And if you can do this for different vibrational bonds, then you can basically piece together what different parts of the molecule look like at the surface. And a very, a lot of richness understanding comes with putting this together with an idea of what the surface structure looks like, if you've characterized that ahead of time, or putting this together with what you or others have interpreted the water structure to look like, and you can kind of put these things together to get a holistic view. So what I'm going to focus my talk on today is one aspect of this spectroscopy which has kind of interested us in the last couple of years, and that is that whenever you are looking at candidate structures that could be consistent with what you observe experimentally based on the spectra that you see, there's always a lot of possibilities. And since this is a vibrational spectroscopy, you can do the standard trick, whereas if you can analyze more than one vibrational mode, you can kind of reduce the possibilities a little bit. So instead of 400 possible solutions, you have only 370 possible solutions as to what the structure could be. And there could be more if you could resolve more peaks. But the interesting thing here is that in the end, whatever solutions we come up with, there's always another set of molecules which are exactly upside down and twisted by 180, which we can't distinguish from what we're looking at. And the reason behind this is that it basically talks to the surface specificity of the SFG technique itself. And that is, if you have a functional group on the surface, so I'm just drawing a methyl group at the end of a long chain, for example, and you come in with your 2 fields and you generate some frequency. And if you have another functional group with the same orientation but 180 degrees flipped, so it's pointing out rather than pointing in towards the film, you'll generate an SFG field which is out of phase by 180 degrees with respect to the first case. So these 2 things interfere destructively, and this is the reason why this is such a good probe of surface structure, because in the bulk you'll have cancellation from all of these things, whether it's the bulk solution or the bulk in the polymer film. But this is also really interesting because this means that if you were to have a net population which is more up than down at the surface, so you actually measure an SFG spectrum, it should be possible to work backwards to see which one you have. And you do this by looking at the electric field rather than looking at the intensity. So anytime you want to measure the electric field, you do the canonical thing, which is to do an interferometry experiment. So what we do now is we take most of the visible and infrared laser and we direct it towards the sample, and we need to really give it all that we got because we use really lousy chromophores. They're not chromophores in anyone's definition of the word. Methyl group is not what most people consider a chromophore. And then we take off 5% of the beam, and we direct it into a material which is like the gangbusters star Chi2 material, like quartz or lithium niobate or some kind of piezoelectric material. And then what we can do is we can generate SFG in our sample and in our reference, and we combine them to do the interferometry experiment. And when you combine them, based on observation of whether the interference is constructive or destructive, you can work back to see what was the phase of the field. And the really cool thing is that you could work back to see what the orientation of the molecule is. So there's a lot of schemes that have been proposed to do this. In fact, second harmonic generation has been done quantitatively, interferometrically since the 1960s. But things are a little bit trickier in the non-degenerate form when you're using an infrared beam. But still, there have been lots of nice experimental schemes proposed, particularly for broadband systems. But what we're going to do is we wanted something which was a little bit more robust for our needs, and we wanted something which can access the buried solid-liquid interface, which I'm not going to talk about today because that's kind of a separate story entirely. So what we did is we took our two incident beams and we brought them collinear to each other. So rather than coming at the surface like this, we basically make them collinear. And then we have a piece of quartz in between them. This is what I've labeled as the local oscillator, so it generates the SFG field. And then in between them, we have a piece of glass which we tilt. And by tilting this glass, this is how we run our interferometer. It basically changes the thickness effectively, and we basically change the phase between the beams. And we call this phase shifting unit. Sometimes people think this is the Pennsylvania State University, but it's actually, I didn't even know about the Pennsylvania State University, I'm sorry. So it's this phase shifting unit. We call it PSU. And then by tilting this piece of glass, we can change the phase between the field from our local oscillator and the field which I'm showing you in reflection from our sample. So in principle, this is a very simple idea. What you do is you basically change this phase, and you can see the SFG signal goes down, it goes up, it goes down, it goes back up. So you see destructive, constructive interference. And conceptually, the simplest thing you can do is then take your sample out and replace it with a sample of known polarity and do it again, and then just see how much has the phase been shifted from one with respect to the other. And the simplest experiment is you've got the same type of functional group in a known and unknown orientation. Are they in phase? Are they out of phase? And you say yes or you say no, and you're done. Tricky thing with that experiment is it's hard to have the reference be exactly what you're interested in. But conceptually, that's it. So what we've done is we've basically tilted our glass from minus 45 to plus 45 degrees just to get a bit better statistics. So you see more interference fringes. And the fact that this is a nonlinear pattern, and you can see these interference fringes are more compressed to the minus 45 degree end, kind of makes sense when you think about it. As you're tilting the glass, the relationship between the angle and the thickness is not linear. It gets thick pretty quick when you start getting to high angles. So it looks like this. So what we've done is we were trying to find the expression to fit this for a long time. And it took us a long time to modify what was explained very nicely in the case of second harmonic generation to do this for the non-degenerate case. But once we actually got it, we were pretty excited because this is on the left-hand side, this is our experiment. On the right-hand side, this is the fit, this is the model. And what you see here is this is a two-dimensional interferogram. So along the x-axis, you see the temporal interference, dark, bright, dark, bright, dark, bright, as you change the timing between these two pulses. And along the vertical axis, this is 2,800 to 3,000 wave numbers. Okay, I'm back in wave numbers now. And this is the aliphatic CH stretching mode. And here you see the spectral interference, dark, bright, dark, bright, dark, bright. And when we fit this, we basically can account for all parameters in our setup. We can account for the thickness of the lenses and the fixed optics and a whole bunch of things in the beam path. And what that allows us to do is to take this exact image I'm showing you here and turn it into these spectra, where the top panel is the magnitude of our signal, the middle panel is the phase. And if you have the magnitude and phase, you're basically done. But what we do is we rewrite this in terms of the real and imaginary components. And the advantage of this is because if you can have the imaginary spectrum, you're basically subtracting, or you're basically removing the dispersive part of the line shape. And when you remove the dispersive part of the line shape, there are several advantages. One is that it looks a lot more like an absorption spectrum when you take a look at it. If you want to look at, how the frequency of a mode is shifting with the pH ionic strength, it's a bit easier to see because it's not as confusing. But another interesting thing is if you look at the bottom panel, now your peaks can be positive or negative. And a positive going peak or a negative going peak is what's revealing of the actual polarity. Is your functional group facing the surface or facing the bulk solvent phase? But we need to establish what that relationship is. We can't just automatically say plus is up and minus is down. It depends on what functional group you're talking about, what specific vibrational mode you're talking about. So I'm going to give you our first example. It's a simple example that we took to relate this phase to the polarity, and that's going to be our structural interest. And this is looking at the ester methyl group on the side chain of PMMA, because it's a relatively isolated vibrational mode. So we wanted to basically distinguish these two scenarios, which weren't obvious to us at the beginning, because you imagine you've got a spaghetti-like tangled polymer at the surface. Which of these is the case? And there might be some free energy arguments for some people which could be obvious, but we wanted to spectroscopically see if we could resolve this. So here's what the data looks like. So there's our amplitude of this ester methyl symmetric stretch. and here's our phase information. And then what we did is we compared this to this trichlorooctadecylsilane, which is everybody's favorite molecule for a well-ordered layer with methyl pointing up hydrophobic surface. And what we saw is that the methyl phase from this PMMA ester side chain and the methyl phase at the end of this long alkyl chain was the same. So we wanted to be careful here, though, in terms of making our conclusion that the methyl groups are pointing in the same direction, because the two methyl groups are about as different as you can get for methyl environments. There's 80 wave numbers shift in their two frequencies. That oxygen there puts you in a really interesting electronic environment. In fact, there's been some controversy regarding this picture, because in fact there's such different electronic environments that the permanent dipole moment actually points in opposite directions for those two methyl groups. So what we did is we took this little molecule, this is methyl hexanoate, that we could do calculations on. And although this is small, we're arguing that this ester methyl is probably a pretty good approximation of what a PMMA ester methyl looks like. And at the other end of the molecule, that methyl group, which has got the red set of axes, is probably pretty good for a methyl group at the end of a chain. I mean, it's not a C18 chain, but it's okay. And what we've done is we've basically calculated the relevant elements that go into the hyperpolarizability. And if you look at the last panel here, I'm sorry, I should have brought a pointer with me, but in the last panel is the derivative of the C component of the dipole moment. So the one that's along this bond, right here. And sure enough, there you go. There you see positive values with respect to the normal mode coordinate and negative values. So there's the permanent dipole pointing in opposite directions. But if you look at the slope, negative slope, and all the slopes are the same. And that's what really matters, right, is how the dipole is changing with respect to that direction, not which way it's pointing. So as a result of this, we've now basically concluded that since we have the same sign of the molecular response and we measure the same phase, that the methyl groups are pointing in the same direction. And we thought this result was kind of neat because PMMA is widely considered to be a hydrophobic polymer or hydrophobic material, but it's got a water contact angle of around 70 degrees, so it's pretty darn hydrophilic for a hydrophobic material. And maybe this is kind of molecular level rationalization for what's going on, in the sense that if this torsional angle was turned, so this would be pointing towards here, these oxygens would be more exposed, and maybe we'd see what's more typical for a hydrophilic polymer, 30 degrees, 20 degrees kind of contact angle. So we thought this was kind of neat. But for us, this was kind of a test bed because it was a relatively simple system, isolated vibrational mode. So can we go to some molecule which is maybe slightly more complicated than this? So it's not too bad, right? 583 different residues, 67 kilodaltons. Serum albumin, which is I think I don't know if this is the biologist or the physicist definition of serum albumin, is the protein you look at when you don't know what protein you want to look at, but you just want to have a protein there on your surface. So basically, we wanted to do the same thing. So we wanted to look at serum albumin absorbed onto a polymer film. So we spin-coated some polystyrene onto a film, and then we had a dried sample, because we're baby steps approaching the solid-liquid interface, of this molecule on there, and we wanted to see what do we have from our interference experiment. My keyboard's out of batteries, so I'm having a hard time advancing to the next slide here. And this is our spectrum, which is kind of interesting. So it's kind of tough to know what's happening here, but one of the things that people seem to be reasonably confident about is that this here is where the methyl symmetric stretches occur for serum albumin. And we see this as a clear negative peak in the imaginary spectrum. And this combined with our previous, probably since we've looked at OTS and we've looked at these ester methyls, probably every single methyl group behaves like this. There's other evidence. This is from Tahai Tahara's group at RIKEN, looking at surfactants at air-water interface. When they change the polarity of the head group, it's kind of cool. The water flips, but the ester methyls are always pointing in the same direction. It's pretty well established what happens for methyl groups now. And the fact that we see a negative peak in the imaginary spectrum for the methyl symmetric stretch indicates that these methyl groups are pointing up. Well, at first we were kind of surprised because we have definitely hydrophobic material here. Well, polystyrene has got about a 90-degree water contact angle. But then we kept in mind that, there's not water on top, and our sample is dry, so we have air on top, so the most hydrophobic phase is actually pointing up. So this is just speculation because we really don't know. This is too big of a problem for us at the moment. But it's possible that we've got some kind of confirmation that on an average favors methyl groups pointing up. but we'd like to have some way of approaching this. So what I haven't told you about are some of the tools we've been using to project and understand how we can build up the response for such a complicated molecule. But to benchmark these tools, we thought if we tried to apply this to such a big system, we'd really have no way of knowing if we're okay or if we're totally out of it in our proposal. So we wanted to move to a simpler system. So this simpler system is something which has garnered a lot of interest over the last decades in the spectroscopy community. So this is a 14 residue peptide, and in solution, it forms a really stable alpha helix. It consists of just leucine and lysine residues, but in solution, what happens is this folds into an alpha helix so that all the hydrophobic leucine residues are on one side, and all the hydrophilic lysine residues are on another side. So this forms a face-wise amphipathic alpha helix. And these things are model systems for a whole bunch of things. I mean, one of the ideas is that they can basically form these pores, which can be used to basically drain out cells and work as antimicrobials in this kind of manner. So there's been a lot of interest in this. So here is a list. Actually, I'm missing 4 papers here. These are just vibrational sum frequency experiments that have been done on this molecule. And one of the reasons that piqued our interest in this molecule, not only because we thought it would be a really good model system to use our tools on, is because it has a pretty regular structure. So this is the early experimental data from Summerjai Lab, which got us so revved up about this project. And here what you can see is the SFG spectra of this molecule adsorbed on a hydrophobic substrate, polystyrene, and this molecule adsorbed on a hydrophilic substrate, which is clean glass. And the really surprising thing is on the hydrophobic substrate, they see these aliphatic CH stretching modes, but nothing in the NH region. And on the hydrophilic substrate, they see these strong NH modes, but absolutely nothing, completely silent in the CH stretching region. And what was proposed at the time, a very reasonable hypothesis, is that on the hydrophobic substrate, this face-wise amphipathic peptide lands with its hydrophobic residues down, and on the hydrophilic substrate, it lands this way with its hydrophilic residues down. And that means that as a result of whatever residues are pointing down, these ones are immobilized to an extent where they're not orientationally averaged and they're strong in the SFG. And then the ones which are on the top are kind of dangling around like this so that they are orientationally averaged and therefore silent in the SFG. Well, this is really fascinating for us because we thought that this is kind of surprising because we're not talking about how could you have an isotropic distribution up here? You're kind of tethered onto a backbone of a very regular structure. So we thought there's about 4 reasons why we want to look at this system. So what we did is we did some molecular dynamic simulations. We prepared a whole bunch of different surfaces of different hydrophobicity, ranging from superhydrophobic surface to carboxylate-covered surfaces. And then we basically carried out these really long simulations because it's such a flexible molecule. The sampling is really a pain, and this is only 14 residues. And we watched this thing land on the surface many, many times. And we gathered some statistics. So first of all, we looked at some gross structural details. What orientation does it land in? What's the end-to-end distance? What's the tilt angle when it lands? We also looked at the torsional angles of the backbone on the different types of hydrophobic and hydrophilic surfaces to see how much alpha helical content do we have on the surface, because it could be lost. It could be enhanced. The surface could structure it so that it gets more alpha helical than it does in solution. But what we were really interested in is the SFG spectra. So here's our approach. Basically, we go through all the trajectories in every single frame of the trajectory. If the peptide's on the surface, go through every residue. For each residue, go through every vibrational mode. And is it possible to build up the response in a piecewise manner here? And this is our result. So these are the spectra we predicted. And one of the neat things about this is that when you build up SFG spectra in this way, you can take them apart in ways that you can't so easily take apart in the experiment. For example, we could see what are just the hydrophobic contributions from leucine, what are just the hydrophilic contributions from lysine. And what was first really interesting to us is that we saw that on the hydrophobic surface, we had absolutely no NH stretching signals. So that was really cool. And then we saw that on the hydrophilic surface, where the experiments saw no aliphatic CH modes at all, well, what we saw no methyl CH modes. So we thought that's pretty cool. We did see some methylene, and we're not sure why. Maybe one reason is it's maybe hard, small kinks in the chain, and you kind of see methylene showing up like crazy. So maybe you need more averaging to get all the methylenes out. But we were basically absent in the CH3 symmetric and antisymmetric modes, just like the experiment observed. So then that kind of confidence about that qualitative match lets us look at some things deeper. Now we can look at individual side chains and look at the distribution of all those side chains to see what is the origin of this. How have lysines been averaged to give you that result? How have leucines been averaged to give you that result? And kind of go back and see what kind of structural organization is responsible for that spectroscopic signature. Well, another cool thing about this is that we can, I think I've got a lot of time left here, is that we can go back and we can do something else. And in addition to just taking apart the spectra in terms of hydrophobic and hydrophilic components, we can basically look at residue by residue contributions. So this is some data from Dave Kastner's group at UW, where they've deuterated selectively all the hydrophobic leucine residues along the chain and collected SFG spectra. And we can compare this with what we predict in terms of the aliphatic stretching SFG spectra for individual positions along the chain. So here our agreement's not too bad. In cases where they see big signal, we see big signal. In cases where they see no signal, we see the smallest signal. So we're kind of doing okay there as well. So we're hoping that projects like this will now give us some more confidence of building up the spectral response residue by residue for looking at bigger molecules. We can have more conformational freedom than this pretty short peptide. Okay, I hope that time here includes questions, because I'm pretty much done. So basically, I didn't go through the details of what we do in order to tease out different types of orientation distributions. But underlying that, I've showed you how we can use the phase of the response to look at the polarity of functional groups on the surface. And I always think that at the air-water interface, maybe this is a moot point for some types of molecules, because someone will say, just give me a napkin, I'll draw you right now which end is going to be sticking up in the air, which end is going to be in the water. But at the solid-liquid interface, this is pretty interesting, because if I have a negatively charged surface and I've got a molecule with a big positive charge, I wouldn't want to put more than $5, Canadian $5 even, on which end would be pointing towards the surface. Are the water molecules flipping in between? And because of the water dipoles which are being oriented, now you see the opposite effect. So I think there's a lot of interesting phase polarity questions at solid-liquid interfaces to be answered here. I've shown how you can use molecular dynamic simulations to help get a bit of a leg up on some of these complex orientation distributions when you want to further interpret your spectra. And the last thing I've shown you is how we are pretty successful at building up the SFG response of a fairly complex molecule, residue by residue, vibrational mode by vibrational mode, and getting something which kind of looks like the experiment. So I've got a few acknowledgments here. So first of all, this is my current group, grads in this column, undergrads in this column, who've done all the work, and some former group members who've contributed to this. The next thank you goes to Jerry. Thank you so much for inviting me to this award symposium. It's been a real pleasure to be here and participate in this. And thanks to the organizers for putting this together, and thank you for your attention.
Questions? Please.
Mm-hmm.
The air interface.
Mm-hmm.
So do you account for any phase differences in the two?
Yeah, so I think this two-interface problem is really important because it comes up in a lot of different types of situations. Specifically for the polymer interface, polymer air definitely, polymer water I'll have to see. There's been a lot of work from Ali Nawajala's group, maybe 15 years ago or so, talking about how you can selectively pick up which signal is giving you the SFG, and it's really a drastic on or off based on your beam angles. And if I remember correctly, I think it's if you come in where your TIR for one of the surfaces, you're basically swamping out what you'd see from the other. But in general, what you talk about is really important because there could be many sources of SFG, not just from polymers, but other multiple interfaces.
So do you see it using
should I tell you what we're doing or what we want to do? So we use TIR because it's really hard to give up that factor of 10 or 20 signal when the signal looks really bad to begin with. I always get amused when new students to the group, I get them all excited about the project, and then they see the SFG spectra, and it looks like the lowest res IR spectrum they've ever seen in their life, right? And I'm trying to tell them this is a new technology, right? But I'm considering just getting rid of the TIR as well and taking the hit and signal. And one of the things is that for quantitative work, when you're at TIR, I worry about getting the local field corrections correct, because that local field correction is very steep correction. And if you're not at TIR, you can really have a lot of uncertainty in the refractive index, in the interfacial refractive index. You can have a little uncertainty in the beam angles, and it's not a big deal. So it's a trade-off in terms of. I think everything I showed you here was external reflection, but for the buried interfaces, we've done a lot of TIR work, and it's hard to give it up because it's, do we want to see signal or I want to show you a bunch of horizontal lines, but I think about it too.
Well, let me ask you, maybe I misunderstood. In your studies of the peptide, this is the alpha helical peptide where you have lysines on one side, something else on the other. How did you prepare your sample?
Oh, so that data was all from other groups that I showed you. So we had the BSA data. All the other data was ours in the presentation. But then we wanted to benchmark our tools for predicting spectra. So there's a lot of SFG data for that molecule out there. So I could tell you a bit about how they prepare theirs, but I wanted to clear that up first. Yeah.
Okay, I guess my question is for the peptide, if it's alpha helical and then it's deposited on the surface, why would you expect that you would only see the orientation of one side of the alpha helix?
Oh, I think the hypothesis, which seemed like a pretty good one at the time, is that if you assume that it stays alpha helical, then the hypothesis is based on the fact that whatever side favors the surface interaction is kind of quasi-immobilized. And as a result of that immobilization, you've got all the magic recipe you need for the SFG. You've got orientation, you've got a polarity of your orientation. And the side which is at the top is facing the solvent, so you can have some more movement of your functional groups.
I thought there was no solvent. I thought that the other side was there.
No, that was all in solution. Yeah.
Oh.
So you ask another interesting question. In air, what would you see? I mean, naively, I would have expected to see aliphatic stretching modes and NH stretching modes in both cases. And perhaps, phase resolution would tell you that actually their phases are flipped for different surfaces. But surprisingly, the spectra show a on-off response in those vibrational modes.
So with the bovine serum albumin was the same case, solvent on the other side?
There's lots of data both ways in the literature, but the one I showed you was dry sample, because the buried interface interferometry is another beast. There's something that happens there which I'm shoving under this.
So it's the same question then for the bovine serum albumin. Why are you going to see SFG for the protein air interface?
I think you're seeing SFG from all those interfaces. Yeah.
Then how? I mean, since this is a globular protein.
That's right. Yeah, and there's probably 2-3 layers of that protein down under those conditions. Can't remember what it was. One millimolar solution. So the ellipsometry studies show that there's likely 2 layers of molecules down from the thickness they calculate.
So this is a thick layer that you're studying.
That's right, and it's all SFG active.
Okay, but okay. I can see orientation of the deposited side. Why would I see orientation
Of the next layer?
Yeah.
Well, I guess it depends on the molecule. I mean, for small molecules, it's not uncommon that if there's a big structural change on the first layer, then the functional groups they present up to the second layer is far from the random distribution you would see in the solvent. So I think
this is a giant molecule.
that's right. But I think it's still possible. I think once you have many layers absorbing, I think what you're thinking about would certainly be true. By the time you get to the fifth or sixth layer, you would see no orientation on the downward side. But perhaps for 2 layers, you still see some on the top. So in that case, I just say that the response is from all those molecules.
Other questions?
It's very closely related to the idea about the polymer air versus the polymer substrate question.
Okay, well, let's thank our speaker again.